Maybe I could make horrible instead. I could have saved that. Logarithmic differentiation. Or as I like to call it, logarithmic, because we actually use lons and not logs, but what the heck. How do we find, can we just skip this part? How do we find dy by dx if y is equal to x to the x? Perhaps we can use the definition of the limit, which is 0. Now what? It's like, really? Wow. Maybe the power rule and chain rule combined. So combining power and chain rule. Is this correct? It came out the same, right? If the derivative is the same as the function, then maybe it's correct. Let's check that by graphing.
Oh, yeah.
Should I graph that, or do you want to see it?
Sure.
Okay, hang on. Get out your graphing calculators. Let's set the window -5 to 5 by 1s, and -5 to 5 by 1s. And we are graphing y equals x to the x. And we are doing, I'm just going to do the alpha, this guy here. Whereas the end derivative is 3. d by dx of y1, bars, y bars, enter, where x equals x. Okay, so if they're the same, then blue line should be overwritten by red line because it does not merge the colors. There's the blue line. There's the red line. It's slower, right? Okay. Are they the same? No. Are the graphs same? No. Therefore, we conclusively conclude that they are not equal. What to do now? Logs to the rescue. Logs come to the rescue. And where's the rest of the form? For then, what wasn't here yesterday don't yet have this form. I know not. Hang on. Logs to the rescue. Let y equal x to the x. Take the natural log. So it's natural logs, no artificial logs here. Natural logs only. So ln y is equal to ln x to the x. Now what? Well, so ln y. So what do we do with these?
You can put like the x in front, so it's x ln x. Yo.
Yeah, that's what you do exactly, right? So what's the whole point of logs, right? To use that power. Is it a law or a rule? I forget what. It's both the power law / rule. And the idea is, hey, this way we get to get rid of the exponent, right? We can move it in front. Okay, so we know what ln of y is, right? It is 1 over y prime. And the way I've written the test, there's like 100 of these ln questions, so you better really make sure you know your logarithmic differentiation. And what is x ln x? So this is a product, right? So use the product rule and do the derivative of the right-hand side. It won't go down any further. Okay, so we've got that product x ln x, right? So it's f of x, it's x times the derivative of ln x, which is 1 over x, plus ln x times the derivative of x, which is 1. So what's x times? That's just 1, and that's just ln x. So 1 over y prime is equal to 1 plus ln x. Now what? Well, we need to get y prime by itself, so we're going to multiply both sides by y. But what's y? Well, let's multiply by y. So we'll say it's y times 1 plus ln x. But what's y? Yeah, x to the x. So now we're going to replace the y, right? This always happens in logarithmic differentiation, right? It always becomes y prime is y times, okay, now, but we always have y, or usually have y. So it's x to the x times 1 plus ln x. Graph the derivative to verify. Okay. X to the x, here, I'll slide this over here. So we want to graph x to the, okay, so I'm just going to do y1 bars, y bars. Yeah. Okay, y1 bracket 1 plus ln x. So this is black, so black should overwrite red. Well, that's why I hate this. It's like, or maybe I need to type in x to the x. X. Blue. It's slow. It's got to actually calculate it. I mean, come on. You had to do this by hand. Think of those guys that developed this stuff. They had to sit there and make tables. And
I can do it way quicker than this. They wrote a program. I wouldn't do it right.
yeah, they wrote a program because they had pens and quill. They had quills and ink wells. All right, there. I think it did it that
No, it's
time.
not. No. There's that little circle.
Okay. But the black, there's no red there. The black is overwritten the red. I don't know why the y1 didn't work. If in doubt, replace y1 with x. Graph the derivative to verify. Check. Oops. Check. Okay. Examples. Determine d by dx of x squared plus, x squared plus 2 to the power of 4x, and then find the equation of tangent line to y equals x squared plus 2 to the 4x at x equals 0. So this would be a good written response question, right? The first part of this might just be determine, what's the derivative of x squared plus 2 to the 4x, and you got your 4 choices, right? And anytime you do one of these guys, kind of look at how much work. If it's like a 10-minute question, like a for real 10-minute, not a I was distracted 10-minute question, it's probably not a multiple choice question, right? It's more of a long answer. And the multiple choice should be, they might be 5 or 6 steps, right? I mean, there ain't nothing here that's really just a couple of lines. So they may be a few steps, and that's fine. Okay, so let's set y equal to x squared plus 2 to the 4x. And so what we want to kind of recognize is I have an exponent. I'm going to use logarithmic differentiation. I'm going to take the natural log of both sides. And I would like to shortcut, right? So my next line is going to be 4x times ln whatever. Okay? Anybody shocked by that? It's like, oh, wait. That's how when I'm doing logs aside, it's just the next line just becomes the power is now moved in front. If the power is an expression in parentheses, make sure it comes down as an expression in parentheses. Okay, so what's ln y? 1 over y, y prime. What's this? It's a product, so we have to use product rule. And then there's an inside thing, so we're also going to be using a bit of chain rule there. So do the derivative. Oh, wait. I think there's more. A little out of order on that last term, just because. So after the plus sign, it's always good to leave a little bit of space. because you know you're doing the derivative of 4x, so the 4, so might as well just write the 4 in front as opposed to putting the 4 at the end. Okay, is that good? Now I want to simplify, right? So I say y prime is y times, so we've got 8x squared and we're just going to substitute for y. So we got the expression. So y prime is equal to y, x squared plus 2 to the 4x. Okay, and I think that's good enough, right? You know, you could go with a common denominator of x squared plus 2 inside the brackets, and then you could get rid of it and put that x squared plus 2 to 4x minus 1, right? So if I multiplied this by x squared plus 2 over x squared plus 2, so I could combine these as a single, and the x squared plus 2 became the denominator, then I could remove it by just going 4x minus 1 and then having whatever the top. I'm not going to do it, right? But just be aware that that's an alternate form, right? So if you're looking at a multiple choice answer and you're starting to see, hey, I see an x squared plus 2 to the 4x minus 1, but I don't see any x squared plus 2 in the denominator. Okay, they must have gone with a common denominator, right? And it's multiple choice. At that point, you might just be able to choose that one and not say, you know, like what do I expect? I'm going to see an 8x squared plus 4 times x squared plus 2 times ln of x squared plus 2, right? So you just got to kind of visualize, this is what I would see, and that's kind of what I see there, and so I'm going with this one as the answer, right, as an alternate form. Oh, because we're supposed to do something with this too, right? Oh, right. Find the equation of the tangent line. Well, yeah, I never did that. Okay, so find the equation of the tangent line at x equals 0. So let's go up here. When x equals 0, then y is equal to 0 squared plus 2 to the 4 times 0, which is 1, right? Because anything with a 0 is 1. So the point we have is 0, 1. And we want y prime when x equals 0. So that'll give us 0 squared plus 2 to the 4 times 0, which is y, right? So we've already worked out the y. So, you know, if you're doing one of these guys and you got the y sitting in front here, so you say, hey, I've already worked that out. So 8 times 0 squared to the 0 squared plus 2 plus 4 ln 0 squared plus 2. Okay, so what was 0 squared plus 2 to the 0? 1. And what's this? 0, right? We've got 8 times 0 is 1. So we've got 0 over 2, which is 0, plus, what do we got? 4 ln 2, right? So this is just equal to 4 ln 2. Right? So that's the slope of the line at 0, right? And then we've got the point. So we can now kick up here, right? So the slope is 4 ln 2, and the equation, oops, m in front there. So y minus 1 is equal to 4 ln 2 of x minus 0, if you like. Okay. So y minus 1 is 4 ln 2x. So 4 ln 2x minus y plus 1 is 0. There's the equation of your tangent line at the point 0. Okay, now determine each of the following. Discuss the domain of the function and its derivative, right? So we get got to be aware of this, right? Like what's going on here. Okay, so d by dx. So I always just start off by saying, okay, y equals x to the root x. Okay, now I'm raising it to an exponent, so we can use logarithmic differentiation. So ln y is equal to what? What am I going to write? Root x ln x, right? Okay, so I'm just going to move, if I'm doing the ln on both sides, if you want, you can write ln x to the root x, but you can also just write root x ln x. Okay, and now it's just products and chains and stuff, so we got a 1 over y prime equals, and we do the derivative of this, so we've got root x 1 over x plus ln x times, so that's x to the half, so 1 over 2 root x. Right, that's pretty much it. We want y prime. So that's y times, but y is x to the root x, times root x over x plus ln x over 2 root x. So this can be simplified, right? It can be simplified if we do decide, hey, let's go with a common factor inside, or let's take out a factor. So if we look at these two terms, we'll say, well, the factor, the lowest term factor, we've got an x to the half and an x, right? So and we've got an x to the negative 1/2. So if I take out a factor of, the lowest factor would be x to the negative 1/2. So we can write x root x, that's the y value, okay, times, and I've got the common factor, which would be x to the negative 1/2. Let's put that over 1 for the heck of it. So this will be an x over x, and this will be a ln x over 2. Now x over x, there's no room. X over x is 1. So this, I've got x root x. I've got my x to the negative 1/2. That's a 1, so it'll be 2 over 2. So I'm going to get 2 plus ln x over 2. And then I can combine those two. So I've got powers with the same base. I've got x root x and x to the negative 1/2. So that's x to the root x minus 1/2. So that's just multiplying powers with the same base. I'm going to add the exponents. And 2 plus ln x over 2. Right. Or, and we could even take that 2 out of there and just go 1/2, or x to the root x minus 1/2 over 2 times 2 plus ln x. Or sorry, times, 2 plus ln x or ln x plus 2. X root x minus 1/2 over 2 times ln x plus 2. Right. Now remember, they're all variations of the same thing. Right? It's just how far down do you want to or need to work it. Okay. So it can go that far. Yeah, even stopping here. If you're going to substitute in, I mean, I don't think I'd go beyond this, right? Because it's just, that's a place. I see a place where I can substitute in if I want to, or if I need to. Discuss each one. Discuss the domain of the function. So what's the domain of x to the power of root x? we got a square root, so it's got to be greater than or equal to 0, right? We can do square root of 0. So the function itself, so a function, well, greater than or equal, so 0 is positive, and the derivative, almost, but it's not a square bracket. We can't include 0, right? Because you can't do the ln of 0. Okay, so I think the derivative will be 0. So the function includes 0, but the derivative itself does not include 0. Okay, ready for B? And remember, all of this stuff down here is just, window dressing, just icing on the cake, just changing the form. So showing you, this is what's possible, but hopefully it won't be. So I better start this one way up here. Okay, so logarithmic differentiation, right? You've got an exponent. And it's not a number, right? I mean, if it's x squared, you're not going to use logarithm, although you can. We'll do one of those later. All right, so it just becomes, oops, don't jump too soon. So ln y is equal to sine x ln x, right? Because I got variable in the exponent, fine. We're just going to use logarithmic differentiation, right? We'll take the ln, natural log of both sides. Derivative of y, ln y is 1 over y prime. Okay, that never changes, right? In logarithmic differentiation, left side's always 1 over y prime. This always ends up as a product, right? It has to, because you brought down the power, right, as a term. So now you've got a product. So you're always going to use product, and then probably chain rule if need be. Okay, so product, so it's first function. Plus, and then one of them is always the ln of x, right? Times the derivative of sine, which is cos. One more line here. It might be worth combining these guys, right? Getting a common denominator. So that'll be sine x plus x ln x cos x all over x. Okay, so we're just going for common. So we've got to multiply the ln x cos x by x over x. So we've got a common denominator. And then y prime is equal to, what is it? X sine x? X to the sine x. Okay, we got powers with the same base, right? That's an x to the negative 1. So we get x to the sine x minus 1, right? So this guy down here is really an x to the negative 1 multiplied by x sine x. So we get x to the sine x minus 1 times sine x plus x ln x cos x. It's always the question of if it's multiple choice, and that's the final answer. So a lot of us at some point look at the multiple choice answers and say, okay, what form are they in? Like, what do I see? And then just say, how am I going to get there from here? Okay. Yep.
Can't you cos sine x, make sine x over x?
Yeah. Just that's limits.
Yeah.
There's a limit to what you can do, and it's limits. But it's on your formula sheet. What's the domain of x to the sine x? any real number, really, right? Because we do the sine of any number, and we can then take x and raise it to that power. So function, and what is the domain of the derivative?
Same thing, yo.
Maybe you're doing a ln x, yo. There's a ln x. Yeah, so what's the for reals domain? It's got to be positive, right? So 0 to infinity. There was some discussion in math teacher circles about, so when you're doing that, should you really be doing absolute values when you're taking the log on both sides, right? Because as soon as you take the log, you're saying this thing has to be positive. And it turns out that, yeah, you can, but in the end, it doesn't matter. It really does. Really, the domain of the derivative ends up being the same as the domain of the original function. It just, except maybe 0. What's next? X to the e to the x. How much space does that? Oh, somebody change. Yeah. Okay. So maybe we'll do that one down here. Let's do that. Okay. Tell you what. Let's do d first, and then we'll see what kind of room we have. You probably squeeze stuff in, so you're good. But I'm going to do d next. So cos x to the x. Okay. So just start off by saying so y equals. Okay. Then. Didn't we just do that? No, because the sine x above was the exponent. This one is the, okay, 1 over y. So x times 1 over cos x times minus sine x. Too many brackets. Okay, so the derivative of ln cos x is 1 over cos x times the derivative of cos x, which is minus sine x, plus ln cos x times 1. And does that simplify? I'm sure there must be some simplifying here. Y prime will be, so what's y? Cos x to the x. And what do we got here? So I've got an x and I've got minus sine over cos. All right, so maybe, but if I got a cos x here on the bottom and I got a cos x here, so maybe I'm going to be premature with that. All right, so you look at it, you say, okay, I've got a cos x to the power of x, and I've got a cos x in the denominator there. But maybe we just leave that, make this what? Minus tan x? Let's try that. So we've got x times minus tan x plus ln cos x. And now we'll just pull in the, so it'll be cos x to the x. And let's lead with the positive term, so ln cos x minus x tan x. That's probably good enough. Could you clean it up a bit? If you put a cos x in the denominator here, and then you could subtract 1 from that. Okay. Variations. All right, so now we can do C, where I have room. So y equals, what was it? X e to the x. All right, give it a shot, see what you get. Step 1, take the ln of both sides. When you do that, move the power out front. Step 2. Take the derivative of both sides. Right, what am I doing? So ln 1. That's right, that's like an e to the x. I didn't write that very well. Yeah, this is c. Yeah, I took a down way into c, so now I'm doing c over here. This is c. Yeah, okay, so e to the x times 1 over x plus ln x times e to the x.
Instead of 1 over y times y prime, couldn't it just be y prime over y?
Sure. For some reason, I just like to write 1 over y, because I know it's moving over, right? It's fine. But yeah, y prime over y is fine. It's the same thing. Yep.
Is it okay if you just write the y at the beginning of the
I think you need to go here, and then you can move it over. Okay? It's kind of like, I think I'm just going to leave this here while I simplify this, right? So if I look at this, I could say, if I throw an x in front here, I can put an x on the bottom here. And I can pull a common factor of e to the x over x out of this. Okay? So I'm going to do a couple of things. I'm not really going to show a lot here. So I can put this over x by putting an x here. Okay? And then I can say, all right, so I have a common factor of e to the x over x. So e to the x over x. This is going to be a 1, right? So we could write 1 plus. And this will be an x ln x. Okay, and now I'm going to do y prime equals, and I'm going to. So 1 over y, so it becomes y. So now it's x e to the x. I'm not writing that very well. X e to the x times e to the x over x times 1 plus x ln x. Must extend page. Okay, common base. This will be a negative 1. We're just going to subtract 1 from that. So we've got x to the e to the x minus 1 times e to the x times 1 plus x ln x. Okay, yeah. How do we do this as multiple choice? A lot of times multiple choice just say find the value of the, y prime when x is 0 or x is e or x is 1 or something. At which point you're not necessarily carrying it down too far, right? Like I don't need a really simplified form of the expression if I'm just going to be substituting a value. Okay, like at some point I just need, like take this, or even this, and multiply it by x e to the x. Right. If I'm going to substitute in and just evaluate it, that would be just as easy. 5x to the x minus 1. So ln y equals. So most important step here is when you bring the x minus 1 in front as a power, that you bring it as an expression, right? That you put parentheses around it. Okay. So this coming down here has to be an x minus 1. Then so it's x minus 1 times 1 over 5x times 5. Okay, I'm just going to. So we know the derivative of ln 5x is 1 over 5x times 5. So I'm just going to write it as 5 over 5x. And then they're going to cancel. This will just end up as 1 over x plus ln 5x times 1. Write that in or not if you like. This is just 1 over x. So let's go with a common denominator. So common denominator is going to be x, so I'm going to have an x minus 1 over x. Already got that. So I need a plus x ln 5x. Okay, so I think I'm good there. And now we'll bring the y. So y prime equals, so I read y, but just so 5x. Okay, this could be, so what do we got? X plus x ln 5x minus 1 all over x. So one more line, right? Because I got an x on the bottom, I got a power of x. So, you know, again, so it'll be 5 to the x minus 1, x. So x to the x minus 1, but that's an x minus 1. So x minus 2. Now this is gone. So we just got x plus x ln 5x minus 1. We don't need a horrifically large set of brackets there. Okay. So again, what you're looking for is, when I'm doing these as multiple choice, before you get too far into it, look at the answers and just sort of say, what am I aiming for here? Like, you know, I need something that looks like, or that is one of these 4 guys. One more thing. I got a smidge of room. What if we say y is equal to x to the n? We already know the derivative of that, right? But what if you use logarithmic? So you say ln y is equal to n ln x. So 1 over y prime is equal to, so it's n times 1 over x, right? So y prime is equal to x to the n times n over x, or y prime is equal to n times x to the n minus 1. Right. We know that. We've done that one before, right? But you can do it with logarithmic, right? 1, hey, that handles exponents. I just think that's kind of neat. Right? It's just an alternate way of showing that y equals x to the n is n times x to the n minus 1. It's cool. Determine the equation of the tangent line to y equals 2x plus x squared plus 2x plus blah, blah, blah. Okay, wait a sec. So I can do the derivative of 2x pretty easily, right? And I can do the derivative of x squared pretty easily. And I can even do the derivative of 2 to the x pretty easily. And the only place I really need logarithmic differentiation is for the x to the 2x, right? So we could say y prime is equal to d by dx of 2x plus d by dx of x squared plus d by dx of 2 to the x plus d by dx of x to the 2x. Okay, now I wouldn't even bother writing that down, right? But I bothered. Just show you, right? It's just a sum or difference of derivatives, right? I mean, so we just could take, so let's say, all right, what's the derivative of 2x? So this is 2 plus, what's the derivative of x squared? 2x plus, what's the derivative of 2 to the x? You look on your formula sheet. So what's the derivative of b to the x? B to the x. Is it over ln b or is it, no, times ln b, right? So it's 2 to the x ln 2. Plus, now we're going to use logarithmic differentiation, right? but just on this. So maybe we just go over here, we just say y is equal to x to the 2x. Ln y is equal to 2x ln x, ln y. 1 over y prime is equal to, wow, you left yourself a ton of room here. So it's 2x times 1 over x plus ln x times 2. Leave yourself more room here. This says ln x times 2. 1 over y prime is 2x times 1 over x plus ln x times 2. So 1 over y prime is equal to, so those cancel, we've got 2 plus 2 ln x. Y prime is equal to x to the 2x times 2, well, let's pull the 2 out as well. So let's say it's equal to 2, common factor, y, x to the 2x, times, let's write it as ln x plus 1. Okay, or 1 plus ln x, it doesn't matter. And let's fill that in here. Plus 2x to the 2x times ln x plus 1. Okay. So the only expression there, you could have done logarithmic differentiation for the whole thing, right? You could have done the ln of 2x plus the ln, and so on, but you don't need to. Okay, what did we want? Well, we wanted y prime, like, I'm not going to simplify this any further. We're just going to substitute in an x equals 1. So y prime when x equals 1, so it's 2 plus 2 times 1 plus 2 to the 1 times ln 2 plus 2 times 1 to the 2 times 1 ln 1 plus 1. Okay. Now all we've done is gone through and just everywhere we see an x, we've stuck in a 1. Okay, so what do we got? 2 plus 2 plus 2 ln 2 plus 2 times 1 to the 2, which is 2, times, what's the ln of 1? 0. Okay, so what do we got? We got 2, 4, 6.
Shouldn't it be 2, 1, it's 4. Yeah.
What? What did I do?
You dropped the square on the last one term. Yeah.
This? 2 to the x, 2 times 1?
Which is 2.
Yeah, what's 1 squared? Usually 1. So, just going with the commonly accepted value for 1 squared.
It never hurts to
Right?
mix it up.
No. I mean, I wrote it in. I wrote 1 to the power of 2 times 1. And then when I went through and evaluated, I just said that's 1. So we got 2 times 1 times, ln 1, wait, that's 0. Plus 1. So we got 2 plus 2 plus 2, and then we've got 6. So that's 6 plus 2 ln 2. You could factor it, go 2 times 3 plus ln 2. Do we need to? Or are we trying? Oh, of course, because we're trying to find the equation of the tangent line to the curve at x equals 1. Okay, so we've got the slope, right? We need a point. So when x equals 1, y is equal to 2 times 1 plus 1 squared plus 2 to the power of 1 plus 1 to the power of 2 times 1, which is still going to be 1. So 2 plus 1 plus 2 plus 1, which is 6. So we have the point 1, 6, and we have the slope. So y minus y1 is m, x minus x1. Y minus 6 is 6 plus 2 ln 2. Okay? Put parentheses around that, right? Because that's a single, it's really just a number. You could work it out, but we're not going to. X minus 6. So y minus 6 is 6 plus 2 ln 2 x minus 6 times 6 plus 2 ln 2 So what do we got? 6 plus 2 ln 2, 6 plus 2 ln.
Yeah, x minus
x
y
minus 1.
not x minus 6.
Right. Fling.
Also, you're missing
I don't doubt. What happened to stuff? Okay, hang on. X. Okay, x minus 1. So we've got this minus
more
this,
parentheses.
where. So that times that is that. That times that is that.
Oh, I see.
So I need to. So I'm doing this. So this, that's there. Okay. Minus y, minus no plus 6. Is that this is positive? I think. Well, yeah, it's positive. Plus 6 plus 6 plus 2 ln 2. So that's a 12. Like equals 0. All right, so I guess one more. 6 plus 2 ln 2 x minus y plus 12 plus 2 ln 2 equals 0. Wow, it looks nothing like what I have here, but I might have. Y minus. Yeah, must have blew it when I did this. Oh, right. No, what about, that's minus 6, isn't it? Minus 6 minus 2 ln 2. Okay. So 6 minus 6 is 0. Minus 2 ln 2. Good. You're better than the 20s because they pointed out the error after I stopped the recording. Which means I now have to go to YouTube and annotate. Okay. Oh, God, really? What time is this thing? 19 minutes, all right. Just keep hammering away. Logarithmic differentiation is also very useful when finding derivatives of functions and relations that are expressed in factored form. And a big question becomes, when do we stop? And we're just going to stop pretty early in this, okay? Okay, so if y equals this, then ln y is, this time I'm actually going to write the ln of the whole thing. So I think, what's my alternative, right? Alternative is we could use the quotient rule on this, right? So we could do x squared minus 9 squared times the derivative of that product, right? Because that's a product up top. Minus the stuff that's up top times the derivative of x squared minus 9 squared, all over x squared minus 9 squared squared, right? And you just sort of imagine that, you know, do I really want to be doing that? Because what does logarithmic do? Well, we take the ln, so we got 1 over y prime is equal to, okay, so this is going to be 3 ln 2x minus 4 plus, right, because if you're multiplying, what do you do with the logs? You add them, right? Plus 4 ln x cubed plus 8. What's the next sign? Minus, right? Because you're dividing. So minus 2 ln x squared minus 9. So if you think about it, what does it take to do the ln of, 3 times the ln of 2x minus 4? Not much. So 1 over y prime. Now we know what y is, right? Y is just this. So we're ultimately going to end up with that expression in brackets stuck in front of what we are now working out. Okay, so this is going to be 3 over 2x minus 4 times 2. So I'm just going to write it as 6 over 2x minus 4, right? That's where that's coming from. So it's 3 times 1 over 2x minus 4 times the derivative of this, which is 2. So I'm going to write 6 over 2x minus 4. Okay, the next one, it's going to be 4 over x cubed plus 8 times what? Times 3x squared. So instead of writing that, we're just going to go, hey, I'm going to have a 4 and a 3x squared up top, so I'm going to write 12x squared. Now, do you want me to just write that, or should I just go through and do the 3 times 1 over 2x plus 4 times 2 and then? So, preferences? More detail, less detail? Less? Okay. So less detail is saying, all right, I'm going to put a 4. So I'm not going to put this yet. I'm going to put a plus. I'm going to go 4 over x cubed plus 8 times 3x squared. So 4 times 3x squared is 12x squared. Minus. Okay, I'm going to put the x squared minus 9 on the bottom. I've got a 2 times 2x, so that'll be a 4x. Okay? That's where it's coming from, right? Just remember, there's two things going on there, right? There's both just a constant, and then there's the chain rule being applied. But those are really easy derivatives to take, right? As opposed to 2x minus 4 cubed as a product with, I was doing the product rule with. And so y prime is equal to, so here's where we're going to stop. 2x minus 4 cubed times x cubed plus 8 to the 4th. Oh wait, we gotta flip this, right? Oh no, it's y. Okay, we don't have to flip this, it's just y. So 2x minus 4 cubed times x cubed plus 8 to the 4th over x squared minus 9 squared times 6 over 2x minus 4. We could simplify that if we wanted to, right? I mean, they're all even, so we could say 3 over x minus 2 plus 12x squared over x cubed plus 8 minus Now, you could go on. Don't go on. You could go on, right? Because you can find a common denominator here and get a single term, right, with that common denominator, pieces of which are going to cancel with this. So actually, really, we should have left that as a 2x minus 4. If I was going to go for a common denominator, I'd want to leave that as a 2x minus 4. Maybe I'll put it back just to say, if you wanted to go with a common denominator, so 6 over 2x. Because then part of that common denominator, right, the 2x minus 4 component of the denominator is going to take that down to a squared. The x cubed plus 8 component of the denominator is going to take that down to a cube. The x squared minus 9 part of the denominator is going to make this an x squared minus 9 cubed. And then there's going to be a pile of stuff up here, right? But we're not going to, there's like x to the fifths in there and stuff like that, right? It's just, it's doable, but at that point it's really just an exercise in algebraic manipulation. At which point you might as well let a computer do it, seriously.
So why can't we use calculators then?
Because we're not going to ask you to go that far, right? Like, you just leave it as that, right? Like get that, simplified, stick the y in front of it, and say, done. Same deal here, right? Determine dy by dx is the same exact idea. So, we're going to say up here y equals. So I just might say 4x squared minus 1 to the half. The reward for sticking it out is pie and ice cream.
Can't we just stop now and get a head start on
Oh,
the ice cream?
how hard is this to do? Like, seriously, it's not that hard. Right? It's a little manipulation, but it's not a hard thing, so do it, right? Like, practice. If you're going to do the part where I'm going to do the 1/2 times and then use the chain rule and the 8x, and I got to say an 8x, I'm going to 2 down here, and I'm going to put a 4x up top, then do that, right? I mean, do that manipulation. And then look up here and see if you agree, and if you don't, figure out which of us is wrong. And we might do some partner quizzes, right? In which case, I always figure if you're going to convince the other person that they're wrong and you're right, you really better be right. It's really embarrassing if I convinced you to put the wrong answer down. How did you let me do that?
I did that.
Yeah.
You change and recorrect to maybe still wrong. Well, it's their fault for listening. Yeah, I got the 86 on that. It's not it's like my second worst test all year.
Okay, so there's your first line. And we're not taking it far, right? So we're just going to do the thing and then put the y out front and then. Okay, so I got a half over this times 8x. Okay, and I've got a 3x squared, so 6x squared. And I got a 6. Okay, that's about as far as I'm going to go with that. And so one more.
The 2x minus 5 there is 2x plus 5. Big changes, right?
You know, I'll tell you, I might not even see it on your paper. Like you might potentially have that wrong. You may or may not.
It's like a mafia. Yeah, is it
Well, where that would manifest itself is if we were carrying this further and actually combining, then all of a sudden, yeah, it's just going to be way out, as opposed to this just has an incorrect sign in one little thing. It's like it's almost a half, or it's just I blink and just stick the plus sign in, circle it, and say, hey, this was a plus. Yeah, you know, like it's almost not worth a half a mark because it's a copying error, right? Like it's a transcription error. So the bridge falls down, but you know. Okay. I don't know. Is it? No, because it's a half. It's a half times 8x, right? 1/2 up top, 8x.
Oh, I included a 2 at the bottom.
You can do that, and then just come down to a 4x eventually.
dumbass?
So, you know, you might show more work. Like it might look like 1/2, and then an 8x up top, and then a 4x squared minus 1 on the bottom, and then a 2 over x cubed minus 1 times 3x squared, and then a 3 over 2x plus 5 times 2, and then you combine it on the next line. So it's whatever you're comfortable with, right? And as you do questions and you're checking your answers, it's like if you're always making a mistake, you're like, hey, I can do logarithmic differentiation really well, but I keep getting the numerators wrong. Then step back, take more steps, right? Like that's all. So on a test, if you're running out of paper, space, whatever, just come get a sheet of paper and do it on there, and then just reference it, right? So we'll staple it onto your test and just say see attached. And on the attached, please put, like if it's number 5, clearly say here's number 5, here's my solution. Okay, or continued on attached page, in which case you put number 5 continued, and you finish it off. Okay, so whatever, I don't mind. I don't have this. I hate when you use scrap paper, but if you need to, use it. I mean, calculus takes a lot of paper. I have a notebook at home filled with, over the previous summer I went through and redid. Well, I sat down with Stuart's first year book and just went through it. So, what are they going to have to do next year? All right. Is that it? That's it. Is that it? There's nothing more on the page? Oh, thank God. And we're done in time for 5.